Alright, hello everybody, and welcome back to what we're going to be going over now is part 2 of homework 4, where we are going to be minimizing the Frobenius norm of the Broydens. So this term right here, we're going to minimize it, and that's what's going to give us his version that's displayed right here. So, bring back OneNote. So, what we are doing is we're minimizing the updated k plus 1 minus the original Jacobian, and we're minimizing that. So the first step in doing this is, if you recall, Broyden used a Sherman-Morrison formula to update the inverse. Now we can use that same format for updating a matrix. The outer product of UV, two vectors, as such. So, we want to minimize this term, this expression. We are also minimizing our two vectors for our update matrix. So, when you look at this, when you're calculating the norm of an outer product of two column vectors, UV, what you are saying is you got your U1 times your V1, your U1 times your V2, your U2, your V2, and that goes on for however many rows each of them have. That's what it's looked like. So what we can do is, when we want to take the norm of that, that turns into a summation where you add U1 V1 plus U1 V2 plus U2 U1 V3, so on and so forth. So it's actually a double summation, where you have your i's and your j's. So for ui, ej. And since it's a norm, that's getting squared. Like that. So that's where we stand right now. So what we got to do now is we need to set up a constraint. So to do that, our constraint equation is going to be this. Fk plus 1 has to equal Fk plus the updated Jacobian matrix multiplied by our change in x. Now notice the Jacobian there, we have the equation for it up here, so we can substitute that in. All I'm going to do is I'm going to flip this over to this side and make this our delta F. Equals Jacobian K plus UV transposed times delta X. So what we're going to do with this equation is we're going to solve for u. So what we do is first got to distribute x with delta x. Because keep in mind, delta x here is a column array, or a column. So our change in f values is equal to jk delta x plus uv transpose delta x. So you can get rid of this on this side by subtracting it from our delta f. And then, since this is now an inner product, v transpose multiplied by delta x, that's just a scalar at that point. So we can divide by that. So v transpose delta x. And that is our u. So we got that. So if we go back up here to this equation, we bring it back down. We got the double summation still of I and j. Here what I'm going to do, just so I don't have to write out each time, I'm going to rename the numerator up here to h. So we have hi squared, hi squared times vj squared. All of that is divided by the summation of vt delta x I. And then this is also squared. So, with that, what I'm going to do now is we got to now minimize it. So, when I say minimize it, what we're going to do is we're going to take the partial derivative with respect to vector v, give it a subscript of m. So vector v at m indexes, where m is just the index, such as 1, 2, all the way up to n. Of our double summation I squared v j squared over summation v transpose I delta x I squared. And that has to equal 0. So what we have is we have two functions here, so we got to use chain rule, got to use product rule. So first up is differentiation by parts. So the first term we're going to look at is up here, where we're taking it with respect to v, vector v sub m. So up here we take the derivative of this. First thing we got to do is we got to take the 2 down. So 2. So now that becomes a 1. But we're still going to have each element of h right here. So it can be multiplied by that v, because h, in this case, since we're just looking in regards to v, is constants. So that won't change with v. Squared. And then, based on the power rule, that now becomes Vm to 1. Then we also got the sum of V squared delta xi squared in the bottom. Now we got to differentiate the bottom part. So in the denominator, raised to a second power is the same as raising it to -2 if it's above the line. So it'll be -2 times the double summation of hi vj squared over the sum. Now keep in mind, we did power rule, so -2 minus 1 is -3, so this becomes a 3. So we got vi transposed. I need to write that there too. And delta xi squared to the third. Now, there's also chain rule happening in here, so we also got to multiply by delta xm. And that is all equal to 0. So, what we notice first is you can get rid of that 2 right away. We also got the sum of h sub I in both terms, so we can take those out and get rid of them. Now, we also got the, let me just rewrite these part right here, make it a little easier. We got v transposed delta xi squared. So we got this squared here, got this cubed here, so we can remove this and remove that and change that to a 1. So what we're ending up left with is Vm minus the sum of the v's squared over the sum of the transpose of v multiplied by our delta x vector. And all that times delta x sub m. And that has to equal 0. So, what Broyden did, that's kind of genius here, is he knows that this vector v and that this vector x, delta x, are going in the same direction. So, you can have another vector, which we'll just call alpha, and that will get you your delta x. Or that will translate your delta x to v. So with that, if we plug this expression in for v, we get is alpha delta x m minus the sum of alpha squared times delta x m squared. Keep in mind, alpha is constants. And then we also got the summation of v transpose. So we get alpha got delta x m squared. So these cancel out. This cancels that out. And we're left with delta xm. So when we get down here, now I have alpha delta xm minus alpha delta xm. And then that equals 0. So we know that this constraint is true, no matter what. There. So since we know that is true, can do is go back here to the original matrix update equation. So jk plus 1 equals jk plus uv transpose t. So we know that to be true. But now what we can do is we can exchange u and v for these other equations here. Right. So do is this now becomes jk plus, now the equation for u is, where is it? Right here. So the equation for u is right up here. It is h divided by v transpose delta x. And you multiply that by v transposed. Now we can plug in this for v. Now I got j sub k plus h over alpha delta x transpose delta x. Now remember when we did the first part of this, delta x transpose times delta x is the same as just saying the norm of that squared. Because that returns a scalar value, because it's an inner product. Actually, I think I screwed up somewhere up here. Yeah, so yeah, so right here. So yeah, so this term v transposed. Yeah, so that means delta x is transposed here as well. So this is actually alpha delta x transposed delta x. Now, of course, this still goes to delta x squared, so that will still cancel out. But the way I just wrote it down here is a little wrong. But back to here, alpha delta x transposed. So the alphas cancel out. Now let's go ahead and bring back the values from h. Jk plus h is change in f minus Jacobian k times change in x over the norm x squared times change in x transposed. So now if we go back to Broyden's, look at his version he found, that's how his came up to be this. And although ours from part 1 looked a little different, let's find ours. Yeah. Even though ours looked a little different, we found that it equaled the same thing. But this is how he got his version. He just went about it a different way, which could be more applicable, especially for what we're about to do. So, now we solved it to show that the theory works. Now, let's take that minimizing idea, where we're going to minimize this function. J sub k plus 1 minus j sub k. And we're going to constrain it by saying f of k plus 1 equals f sub k plus j sub k plus 1 times change in x. Now we're going to constrain it doing this, but what we're going to do is we're going to sort of rewrite it to match this. So instead of doing it like that, let me think about this. Let me think. So just like we did before, is this still recording? Yeah. Well, just like what we did before, j sub k delta x. Just like we did before, we have another system of equations here. Now we subtract this from this, so get f sub k plus 1 is equal to f sub k at minus f sub k is 0. So we get the j sub k plus 1 minus the j sub k multiplied change in x. So this is our constraint equation, to where as we minimize this function has to also be true. So let's go ahead and head over to Colab one more time. Close that. And let's go down here. What we're going to do is we're going to have a jack update function. what we're going to need for it is our j sub k plus 1 is what we need to find, but we have to have an old j sub k. I'm going to call this j old. We also have to have a f k plus 1 and delta x for our constraint. So do dx, then new f, or well, f new. What we'll do is our objective new equals dot reshape j old dot shape return jnp dot sum j new minus j old squared. So that's our objective, where we're going to minimize this to get as close to 0 as we can, while also obeying our secant constraint. Shape shape turn j new minus j old, or that by dx. Then we are going to subtract that by our f new. Now the reason we're doing it like this is when we plug it into our scipy.optimize stuff, our constraint has to go to 0. So to do that, we have to rearrange it a little bit, such that j sub k plus 1 minus j sub k multiplied by delta x subtracted by the new f value will get us 0. So we got our objective, we got our secant. Now all we gotta do is we go up here, need to import it from scipy.optimize, import minimize. Okay, everything's working as it should. So just to test this out, let's set j old to let's just set to an identity for now. Let's do 3 dx, do a jmp.array, and let's set that to, let's say, 0.5, 0.8, 1.2. And let's reshape that so it's a column. And then same deal with f new. Set this to say 0.8, and then let's do 2.5. Same deal, let's reshape, -1, 1. So we got all that. So now we go to jack update j old dx new. Realize I need to actually return something. Minimize our function. We want to minimize the objective. Our x naught, let's just do jold.flatten. Method, and then the only thing I'd add now is constraints. Dict type will be equation with the function being our secant. Run this, and we got an error. Oh. Squeeze. This has to be a single dimension, I believe. Yep. Alright. So if we do res res.x b shape shape. So there we got our result from this method of updating. Now, if we try doing what we found in the first part, it's an ARM method here. We scroll down till we get to right here. Right, so we do ARM method, see what happens now. J_old plus, right? Then in the numerator, we got fnew, matrix multiply by the transpose of dx. Divide that by dx dot transpose dx. If you notice, 1.214, 1.214, 0.1716, 0.1716. All of these are matching up, showing that this method will get you the same result as this method. To reinforce that, what I'm going to do now is I'm going to copy the Broyden we made in our first part, except this time I'm going to change this to minimized. So instead of J inverse like that, what we're going to do J inverse equals jnp.linalg invert J. Go through. And instead of doing it like this, what we're going to do is we are going to use that jack update that we've made. J equals jack update, with J_old being our current value for J, our dx being that, and our fnew being f2. And J inverse jnp.linalg.invert J. So if we do that, go up here, copy this, bring it down here. Now instead of doing normal Broyden, if we do Broyden min, see what happens. Oh, I think I have to reshape F2. Let me try that. X dot reshape J dot size shape. Let me try that. Alright, now if we do that, look at xres, got 5 and -2. Go back up here. 5, -2. So then if we do that up here, xres is 25, -7. 25, -7. But, so they may be different values, but as you can see, they're still solving it just fine. So, just go back down here. So that, as you can see, both methods work. And then with that, I will see you guys in the next part, where we're going to be going over the final bits of homework 4.